So the covalent bonds that are nonpolar covalent typically occur between two elements of very similar electronegativities. Usually it's your halogen huns, but not always. To give you an analogy of a way to think about this, why it's called nonpolar, is think about if this were a globe, and if this represents the equator, and here you have the North Pole and the South Pole. So North Pole would represent a particular element, South Pole represents another element. They're trying to get stable. They want to get 8 valence electrons. So since they are very similar in their electronegativities, one atom can't pull harder than the other, so they have to share pretty evenly. So basically these two dots represent sharing the 2 electrons at the equator, or 50-50, as I mentioned earlier. They share evenly. So it's nonpolar meaning the electrons are not closer to one pole than the other. They're sharing evenly. This happens like, for example, when 2 fluorines try to bond. Let's look at the electron dot structure for fluorine. With an electron dot structure, what you do is you put the symbol for your element, and then you represent around the atom the valence electrons. Since fluorine is in group 7A, he would have 1, 2, 3, 4, 5, 6, 7 valence electrons. If he tries to bond with another fluorine, that fluorine also would have 7 valence electrons. Keep in mind, every element wants 8, or they want to be like a noble gas. It wouldn't really do any good for one of the fluorines to give the other his valence electron. Because let's say if this purple one gave one to the fluorine on the right, that would certainly make this fluorine happy because that would give him 8. But if this first purple fluorine gave away one of his valence electrons, that would leave him with only 6, and that would make him really sad and not stable at all. So what they do is they just kind of squeeze together, and these guys decide they're going to share their electrons, kind of like putting a puzzle together. So as they squeeze together, no ions are formed here, class, but by sharing and sharing evenly, these 2 fluorines are able to form a chemical bond, and they achieve their octet. So if you were to cover up the fluorine on the right, you see that the purple fluorine has 8 valence electrons now, which makes him quite happy. And then if you cover up the purple fluorine, you see that the fluorine on the right also has 8. They're sharing evenly, 50-50. One doesn't show ownership of the electrons more than the other. So that's nonpolar covalent. They're sharing their electrons evenly. Now, the second type of covalent bond is called polar covalent. You still have 2 nonmetals, but the difference is how they share their electrons. They share their electrons unequally. What happens here? This occurs between atoms that have very different electronegativities. So one of the atoms is going to sort of overpower the other and pull harder, therefore showing more ownership of the electrons. Even though they're sharing, one is a little more dominant than the other. The electronegativity difference is going to be between 0.5 and 1.6 for it to be classified as a polar covalent bond. So let's go back here to my analogy of the North and South Pole. Notice here I've got the dots closer to nitrogen, or I'm sorry, closer to the North Pole than I do the South Pole. This is showing that yes, they're sharing the electrons between them, but nitrogen is pulling harder, or the North Pole is pulling harder than the South Pole. So he has more ownership. So it's called polar because the electrons are closer to one pole than they are the other. They're sharing, just not 50-50. All right, so if you look at up here, hydrogen and chlorine. Hydrogen has 1 valence electron because he's in group 1A. Chlorine has 7 valence electrons. So what they do when they come together, they share. Hydrogen squeezes in close, So that now he has two. Remember, hydrogen gets two valence electrons. He wants to look like helium. He's happy. And then chlorine has now 8. So he's happy too. But chlorine is more electronegative, so he's going to really possess them more. He's going to show more ownership of them, like he's winning that tug of war. All right, so let's look at our electronegativity table and do some examples here. Like, how would we actually figure this out? We're going to classify some types of bonds. So if I wanted you to, well, first of all, let me summarize the ranges of the delta X, the electronegativity difference. If when you subtract your electronegativities, if you get a delta X value between 0.0 to 0.4, then we would call that a non-polar covalent bond. If when you subtract, you get a difference between 1.5 and 1.6, so that's 0.5 to 1.6, that's a 1.6, sorry. That's going to be classified as polar covalent. And then from the notes, ionic compounds or ionic bonding, we said if it was 1.7 or higher, then it's going to be considered ionic. All right, so let's do some examples. We're going to just use this electronegativity table here. So if I want you to classify, classify the bond type, let's look at, first of all, potassium, excuse me now, and I will do chlorine. So you're going to find the elements on the table. Potassium's a 0.8, chlorine's a 3.0. So you're going to subtract. You're going to say 3.0 minus 0.8, and you get a difference of the electronegativities of a 2.2. So if you look over here and classify, 2.2 falls in this range. So that's ionic. Let's look at another example. We look at H and F, hydrogen and fluorine bonding. Find hydrogen, he's a 2.1. Find chlorine, he's a 4.0. So we're going to subtract so that we always get a positive number. So we'll say 4.0 minus 2.1. And you get a difference of 1.9. So if you look over at your range, again, that's higher than 1.7. So you would classify that as technically an ionic bond. All right, let's look at another example. What if we have carbon bonding with oxygen? Carbon's a 2.5, oxygen's a 3.5. So you'll say 3.5 minus 2.5. And that gives you 1.0 for your difference. Classify your bond. It falls in the range between 0.5 and 1.6. That's polar covalent. That means they're sharing but unevenly. I guess it would help if you could see that. Sorry. All right, let's take a look at one final example, example 4. Okay, so let's look at a bond that would form between maybe boron and hydrogen. Okay, so hydrogen's a 2.1, boron is a 2.0. So you're going to say 2.1 minus 2.0, and you get a delta X of 0.1. So your range is in the nonpolar covalent range. Okay, that's it. That's how you use the electronegativity difference to classify your bond types.